Greetings to one and all. Uh, Today we will continue with uh, the second unit of robotics and automation. This is the fourth video under the second unit. So as it's customary that we do that, we show the syllabus, and here we are going to look at more about uh, the grippers and joint notations, etc. There. This was already discussed in the previous video, but then just to have a continuation, we will have this. We have mechanical grippers, we have the vacuum grippers. Let us say for a sheet of glass have to be picked up in a glass factory, we will have a vacuum gripper. We have magnetized grippers for holding ferrous parts. Then we have adhesive devices, and we have simple devices like hooks, etc. Now, here we see a lot of pictorial representation of how the end effectors can hold, and then when during the specification we use things like, whether it is a, if it is open beyond something, we use like a large diameter. If it is small, if the wrist is closing like this, we call it as a small diameter. uh, and Well, if you took an take an extension type, or if we are holding a disc or something like that, how we hold the disc, it's a polymer, or whether it is a extension type, whether the parallel extension and the medium wrap adducted thumb. We have the light tool, ring, disc, five finger sphere grab, etc. There. Now these things will be very much handy when we try and talk about the programming, and then we want how the gripper should move around the object. Okay, depending on the object again. Envelope, we have already seen the envelope, but then here we will look at the work envelope. We will see like how much is can the the robo move uh, and reach the part other than the end effector. Okay. Now this is the work envelope is defined as how far the robo's arm or the end effector mounting plate can reach vertically, horizontally, and backward. So this the entire thing is a volume. It is also called as the work volume. Okay. Now the dimension do not include the additional reach granted by the tools, because this will be ridiculous, because I, for certain things, I can have an end effector which is very long or very short. Now that is customized. Okay, so we don't use, require add that. Any unreachable area beyond the work envelope is referred to as the dead zone. Okay, so you see the internal movement, or where it cannot reach, those places are called as dead zone. Now there is the difference between operational envelope and work envelope, which is something like, will be discussed, or it is important to understand. The maximum envelope determined by the area within the robo may move. There is a restricted envelope. Okay, we put a fencing or something where the operator can come and just place the object and move. Now, in order to prevent the although the envelope is large, we can make the program in such a way that it can move only from one point within that distance. Okay, now so that is called as the operating envelope. Okay, so where the robo will be moving, and the operating envelope is the area of the robo that will be in operation. Okay, so based on that, you can make the movement much restricted, and you will improve productivity, you will increase the time that, by which the robo is okay. So the Cartesian coordinate, or the work envelope, is shown here. It's x y z kind of a volume. It's more of a prismatic one. And then we have something called as the uh, kinematics, that is the forward kinematics and the inward kinematics. It's an important thing that we'll have to understand now. The forward kinematics is the process of determining the position orientation of the end effector in Cartesian space with the help of joint angles. Okay, I move this angle so much, I move the other angle so much, and like that. Each one, the shoulder, the arm, the elbow, the arm, etc. And then I can find the gripper. Now, One that is forward kinematics. Now the reverse inverse kinematics is that given that point, there are multiple ways by which the joints can be the angle can be played or recalculated. Now that is called as inverse kinematics because there are many number of ways by which the same point can be addressed by the gripper by manipulating the shoulder and the elbow angle. So this makes it a little more, complicated. But within the scope of our class, we will just understand this what is forward and then inverse kinematics. Wrist configuration. Now we have come to the wrist. We have finished with the robo. We'll come to the wrist. And wrist, can be moved. You can rotate it. So there are a lot of movements are there. Now there is if the wrist goes up and down, then it is called as pitching, or whether if it is moves left to right, it's called yaw, and then if it is twisted, it's called roll. Now, this gives a lot of degrees of freedom with respect to the kinematics that we look at. The wrist assembly is attached to the end of the arm, okay, and the end effector is attached to the wrist assembly. Function of the wrist assembly is to orient end effector. Okay, the end effector is connected here, and this is attached to the arm. So this part is the wrist part. Okay, the body of the arm determines the global position of the end effector. 2 or 3 degrees of freedom, roll, pitch, and yaw, and the notation that is being given is revolutionary, rotate, rotate, and then the twist joint. Okay, so continue. The joint notations is given like this. Let us understand this. For linear joint, we will use the letter L. Rotational joint R. For twisting joint, we use T, and for revolution, we use V, and then the orthogonal joint, we use O. Now, using these things, we can try and write down like what type of joint it is. Okay. So for the polar coordinate and we have the notation as TRL. So you have the twist, the rotate, and the linear. Twist, rotate, and linear. Okay. So we have already seen these different kinds of configuration, but then we are only looking at the notations. For the cylindrical type, we have um, the twist, linear, and the orthogonal type of movement. Okay, you see the orthogonal type of movement here. Okay, consists of a vertical column relative to which an arm assembly is moved up or down. Now we also have for the Cartesian coordinate body and arm thing, we also have something like a linear movement and then the orthogonal and the orthogonal where it will slide through. Then the jointed arm. So as we said, the hand, etc., the full hand is a jointed arm, very similar to the jointed arm, and it is notated. The notation given to us TRR, which is the twist, rotate, and rotate. The SCARA robo is basically used for assembly purposes. Okay, the name itself implies that SCARA stands for Selectively Compliant Assembly Robo Arm, and it is very similar to the jointed arm robo, except that the vertical axis and are used for shoulder and elbow joints to be compliant in horizontal direction for vertical insertion of the something is, we want to do a vertical insertion, so this hand moves in the horizontal in one plane. Okay, so it's much easier. So today we have seen the various envelopes. Okay, we have seen the forward and backward kinematics. We have seen the different configuration of the wrist, pitch, roll, and yaw. We have seen then the joint notations also we have seen. So with this we will let us stop here for the time being, and then we will continue with the remaining portion of the unit. Okay, thank you very much.